Okay, welcome back, everybody. Um, just a quick note, don't forget today you have exam number 2, chapters 4 through 6. So I open up the session with, if you have any questions, feel free to bring them up. We can go over it. If not, we'll continue with chapter 7. Okay, any questions? I do have I'm scheduled to meet my office hours today with a few students at 3, so you're welcome to stop by at 3 if you have a question there, okay? But like I said, I'm open now. If there are not any questions, I will continue with the chapter. Okay, the test will be basically the same, very similar. You have to 75 minutes, it's time 75 minutes, and it shuts off at 10 p.m. So give yourself plenty of time. All right, then. Well, let us continue with where we ended, which is on slide 12 of chapter 7. There was a question. Yes, there's a question about electron configuration. Yeah, we can do it. We can do that real quick. Let me share the periodic table. Now, what I do with respect to electron configuration is I utilize the periodic table because I can at a glance just get a vast amount of information based on its position on the periodic table. Or alternatively, you can go through that slide that showed you the sequence of filling up the electrons. Okay, so in this scenario, let's cancel. Let's do this. Change the color here. Well, the thing that I do with my periodic table is I number them on the far left, as you can see. 1, 2, 3, 4, 5, etc. Okay. And so that tells me the 7 energy levels of where these electrons exist. The other thing to remember is that in the first energy level, let me darken that up a little bit. In the first energy level, which is the first one, there's only one orbital, and that is the S, okay? And in the second energy level, there are 2, which is the 2s orbital and the 2p. Keep it in mind that this first 2 columns, we consider those as the S block, okay? And the P this block here, we call that the P block. Notice that there are 6 columns here. So we go P1, P2, P3, P4, P5, and P6. Up here, the first 2 in the S, we got the first one, which is S1, S2, okay? So that's how I break up my periodic table, and I have that information here in front of me. So then in the third energy level, we continue with the S block. We also continue with the P, but then we introduce the D, okay? And that's what these guys in here are called, they're called the D block elements, starting with number 21. Now, you won't ever use the D elements until you reach element 21, okay? So if you're not dealing with element 21, you don't really have to worry about the D blocks. The other aspect about the D block is the energy level for those orbits, is that the D orbits, the D electrons for element number 21, even though the element is in period number 4, the Ds start off with 1 energy level less than the energy level that the element is in. So number 21 is in period number 4, energy number 4, but the D orbitals start off with 3D. okay? And it goes all the way across. Then obviously the next one down is 4D, etc. So one energy level less than the energy level that the element is actually in. And then we won't really touch a lot about electron configuration with respect to the F, but being aware that there's 14 of them starting down here. So we got the F blocks here, elements, and sequentially going from F1 through F14. Remember that the 2 points about the orbitals. And that starts in the fourth, the 4s, 4p, 4, oh, there you go. 4 D, and then we got the 4F. Okay, that's where the F kicked in. The F orbitals actually, again, as similar to the D orbitals. The difference is that the F orbitals are 2 energy levels less than the energy level that the element is in. Okay, so starting over here, the 6, energy level number 6, this will be 4F1, 4F2, 4F3, etc. Next one down will be 5F1, 5F2, etc., all the way to 14. There are 14 columns for the F blocks. There are 10 columns for the D block, 2 columns for the S block, and 6 columns for the P. So once I got this picture in front of me, I can, at a glance, very quickly determine the electron configuration for any element on the periodic table. Okay, so with that, let's do a quick one. And let's do sulfur. Okay, sulfur has, keep in mind, you got 16 electrons there. So you keep that in mind, knowing that you got to account for all of them, all right? It is in the P block, okay, specifically 1, 2, 3, 4, P4 column, okay? And that's going to help you with respect to knowing right off the bat how many electrons are in the last set. And it is in the 3rd energy level. That is sulfur is, okay? And so that means that the 1s, the 2s are full. So you can very quickly write in, I wish I had more clear area here. You can write in 1s2, 2s2, 2p6, because that fills the 1st energy level and the 2nd energy level, okay? And we're in the 3rd energy level, so we're going across to sulfur. And so that means that the S block orbital is full. It's in the 3rd energy level, so we write 3s2, okay? Then we jump across to the P block, and we're in the 4th column, so that becomes 3p4, okay? That last energy level is the valence shell. The valence shell is the outermost shell. Sulfur has 3 shells. Shell number 1, shell number 2, and shell number 3. Okay. There's 2 electrons in the 1st orbital, which is this one here. There are 8 electrons in the 2nd orbital, which is the S and the P. And in the 3rd, there are 6, okay, which in the 3rd energy level. And that's how the electrons are distributed. Okay, so that is the electron configuration. When you do that, also keep in mind the driving force for any of these chemical reactions is to get that magical 8. If you look at sulfur, there's only 6 electrons on the outermost shell. So 2 points about sulfur. 1, it is a non-metal. So if it's being a non-metal, it's going to gain electrons. Okay, gain electrons. And it can do that very readily because there are 2 empty spots in the p orbit, because the p can handle a maximum of 6. So it will readily pick up 2 electrons and stick them right there in the p orbital, which then in effect, the sulfur becomes sulfide, okay? And when that happens, now it has 18 electrons by picking up 2, and now it has a -2 charge. And it's isoelectronic with argon because it is now has an element cell, a stable configuration, okay? Much more stable configuration. Elements are trying to get into a stable configuration. Now, if we were going to do chlorine, the neighbor right next to that, same scenario, but that 4 now becomes 5, right? And if we were going to do phosphorus, the one before sulfur, watch, that's only 3, so that 5 becomes 3, the P35. You see how we're doing that sequentially? And if we went all the way across to argon, then that 3 becomes 6, and that is the electron configuration for argon. Okay, and so the main points to remember is first energy level, only 1 orbit. Second energy level, 2 orbits, S and the P. Third energy level, 3 orbits, S, P, and then the D gets introduced. Okay, and then the fourth energy level, we got 4 orbits, S, P, D, and the F. And that every orbit can handle a maximum of 2 electrons. Now, there are just one S electron, but it can handle a maximum of 2 electrons. There's only one S electron, okay? So maximum is 2 electrons in there. There are 3 E orbitals, can handle 6, and there are 5 Ds, can handle a maximum of 10, and there are 7 Fs, handles a maximum of 14, okay? All right, so that's pretty much there as far as with the electron configuration. Is there anything more specific you'd like to know? But with that information, I hope that you can literally grab any element. And, you know, we're not going to do a lot of the D, you know, as far as electron configuration. It might pop up maybe further down the road as an extra credit kind of thing, or the F. You know, once you've mastered the S and the P, you're pretty much got it as far as the electron configuration. Also, you could be asked questions, you know, they give you an electron configuration and say, okay, let's clear this up a little bit. Who would this represent? Let me say, all right, let's say 1s2, 2s2, 2p6, okay? What element would have that electron configuration? 1s2, 2s2, 2p6. Exactly, neon. Exactly. All you gotta do is literally just count the superscripts, because remember the superscripts represent the number of electrons. So you might be given, you know, questions like that, or you could see questions about write the electron configuration for, I don't know, potassium ion, which is not the same as writing the electron configuration for potassium, right? Because the ion would have, with the +1 tells you there's 1 less electron, okay? So be careful when you're asked to write the electron configuration. Verify, am I doing the ion versus the atom? Okay. Or things like, okay, is the potassium ion, who is it isoelectronic with? The potassium ion. Who is potassium ion isoelectronic with? Any idea? Yes, argon. Exactly. Remember, when you have the metal ion, look for the noble gas behind it. And so you see potassium here, behind it would be argon, okay? Because potassium plus, which starts off with 19 electrons, now has 18 electrons, which is the same as argon, okay? Now, who would the bromide ion, which is that guy right here, bromide, who would that be isoelectronic with? Exactly, krypton. So here's bromide, which starts off with 35 total electrons, okay? It has in its outermost shell, it's in a 1, 2, 3, 4. So it's like 4p5, the bromine. And when it becomes an ion, it has room for 1 electron. In fact, everybody in group 7 has room for 1 electron. So that 4p5 now becomes 4p6, and it picked up 1 electron. So now it's isoelectronic with krypton. The important part is it is not krypton. Can't overemphasize that. It is isoelectronic with krypton. Krypton and the bromide ion share the same number of electrons. Okay. So bromide did not become krypton. That's 100% incorrect. The only way bromide, how is the only way that bromide could become krypton? What would bromide have to do to become bromide, to become a krypton? Theoretically speaking, can it become? Sure, but yeah, no, not electrons. Remember when we talked about the subatomic particles, neutrons, electrons, we can lose and gain those all day long. And we don't change, we do not change what the element is. What defines the element? What subatomic particle defines the element? The proton, exactly. Okay. And so in order for bromide to literally become krypton, it would have to gain a proton. And remember, the proton's in the nucleus. So you'll have to find a way to get a proton and shove it into the nucleus and break up all those electron clouds and everything and make it go in there. And yeah, from an energy perspective, it's not impossible, but it's a little tough. In fact, that's how we make elements up greater than 93. We put them through an accelerator and we're bombarding particles and hope that they catch. But you're actually splitting or breaking up or interfering with the nucleus, which contains a lot of energy. That can be very deadly. It's the nuclear bomb. Okay. All right. Well, I hope that kind of helps out a little bit with the electron configuration. And the whole point of the electron configuration is to first get us a good picture on understanding of how the electrons are put in these energy levels based on the fact that they had the emission spectrum that showed the different colors for all the elements that suggested that these electrons are in specific energy levels. Okay. All right. And then from that information, when we figure out the electron configuration, actually explains why certain elements end up with a negative charge and why they're stable there. And for example, like I just stated, chlorine by itself be more of a stable state would love to gain an electron to give you the same number of electrons as kryptons, and that puts it in a more stable state simply because now that magical 8 is around that atom. Because the driving force is to just get 8 electrons around the valence shell. And it's going to either pick up electrons or lose them. Okay. All right, any other questions? All right, well, we just ended up here with respect to, let me back up just one more here. Yeah, we started to get into the bonds. We have two types of bonds. We have ionic bond, okay? Just to refresh your memory, ionic bond, oh, change the color here. Ionic bond and the covalent bond. Okay. Now you would think with chemistry it'd be a lot more, but not really. There's only two types. And the only difference between the two, which you really got to grasp this, is an ionic bond is a combination, it is a compound, which means two more different elements, and it happens to be a metal hyphen or slash interacting with a non-metal. So it's crucial to understand the elements in the periodic table. Who are the metals and who are the non-metals, okay? Because once you look at metal, non-metal, you automatically go to ionic bond. That's the type of bond that is. And that particular bond, think of those as two magnets. You know how two magnets come together because they're attracted? And that's simply because the ions that are generated from the elements have a full charge, a full positive or full negative charge, and they come together with this interaction called an electrostatic interaction. Yeah. Between the two, like two magnets come together. Now, with respect to the covalent bond, that is a combination of a non-metal, Nm, and a non-metal, a compound with two non-metals, two different non-metals. And so here you have two examples where you have carbon dioxide and water, all non-metals. In that particular type of bond, unlike the electrostatic attraction of the ionic bonds, covalent bonds are actually sharing electrons with each other, okay? One of the big properties of ionic bond versus a covalent bond is a real simple thing, is that if you take an ionic bond compound and you put it into water, what happens is they break apart. The ions break apart. So if I were to take sodium chloride, which you all know is table salt, right? And we dump it in water, it literally breaks apart into the ions where you have the positive charge and the negative charge. And those things are the ions and they conduct electricity, okay? Whereas covalent bonds don't do that. There's only one exception, and we won't talk about that now, but we're gonna have a whole chapter on acids. But for right now, covalent compounds do not break apart. So if water stays intact, carbon dioxide, you know, you drink soda pop, a lot of carbon dioxide in my soda pop here, okay? I dump it in water, carbonate the water, it doesn't break up into carbon and oxygen molecules, it stays intact, not forming any ions. So the other difference is, whereas ionic compounds become conductors of electricity, covalent compounds, when we put them in water, are non-conductors, okay, because they don't break apart to form ions, with the one exception, which are the acids, and we'll talk a lot more about those later. So it's crucial that you understand the difference between these two different compounds, because now we're going to get into different properties and so forth, all right? Based on the type of compound that they are. All right, so within the covalent compounds, we have three types of bonds. We have a single, a double, and a triple. A single bond is the sharing of 2 electrons. A double bond is the sharing of 4 electrons, and a triple bond is the sharing of 6 electrons. So what we do, one way to demonstrate that is, let's put a bond between 2 carbons. So I draw a line that line represents, one line represents 2 electrons. So this is a single bond. Okay. Now, there are double bonds within carbon atoms, and there are 4 electrons that are being shared. So this is a double bond, hence I draw 2 lines. Or I draw 3 lines between the 2 atoms, and that is a triple bond. Okay. Now, normally we draw lines for bonds because it's a quick way to do it, but you will see examples where instead of drawing the line, you'll see 2 dots, and that's fine. Okay, so those 2 dots are the same as 1 line that represents 2 electrons. With a double bond, you will find obviously 4 dots. Okay, and with the triple bond, you will find 6 dots. Okay, well, you're welcome to draw dots, and that's fine. Or you, it's quicker and easier to draw lines. But that is what the lines represent. That is a bond. And those electrons in that bond are being shared amongst those 2 atoms. So we have 2, let me redraw this again with the 2 electrons. So these 2 electrons, we have sharing going on. So they're shared with the carbon on the left and shared with the carbon on the right. Okay. All right, now, when we start making these compounds, we're making these bonds, keep in mind, we want to maintain 8 electrons around, with one exception, that is a hydrogen. So let me show you a quick example of that. If we were to draw carbon and then draw 4 lines around it, saying that there are 4 bonds around one single carbon in the center, and those are bonded to a hydrogen. Okay. All right. Hydrogen always has its rule as a duet. You won't find more than 2 electrons around hydrogen. And so if we look at, let me draw the color so we don't change the color. If we look at that bond right here, those 2 electrons are being shared being shared. We'll talk about equal sharing and non-equal sharing here in a bit. Those 2 electrons are being shared with a carbon and hydrogen. Okay. And so I can count those 2 electrons toward the hydrogen and count 2 electrons toward the carbon. So there's 2 of them. Hydrogen's okay. It's shared now. You've got 2 electrons around it. So its duet rule is fulfilled. If we go all the way around carbon, it's sharing a total of 4 electrons with the hydrogen. That is a total of 8 electrons being shared around carbon. Hence, the octet has been fulfilled. Okay. And the duet for every hydrogen has been fulfilled. Okay. And so we don't forget about the octet, even regardless if it's covalent or ionic. That octet is true for both types of compounds that we're going to work with. Right. With respect to bond length, the single bonds tend to be the longest between 2 elements having a single bond, whereas the triple bonds tend to be, shorter. And to exaggerate that, I might say carbon bonded to carbon here versus carbon bonded to hydrogen, to another carbon. That's a triple bond. Now the triple bonds are the strongest, and they pack a lot of energy in compared to the single bonds. A good example would be a single bonded carbon-carbon would be butane. We're all familiar with butane, propane. Notice the ending ane. These are all hydrocarbons. They're made up of nothing but carbon and hydrogen. The prefix tells you how many carbons. We're not going to talk about that, but they're all single bonds. And you see in the lighter, not a lot of energy involved there. It gets hot, obviously, but not a lot of energy. But triple bonds, a good example of that would be acetylene And if you ever cut metal with a acetylene torch, you've got an oxygen tank and a acetylene tank, and you burn acetylene. A lot of energy involved there, hot enough energy to cut right through steel, okay? All owing to the triple bond. A lot of energy packed in it. All right, now let's talk about bond lengths when we got elements coming together. So we have R1, R2. Now, if we look at the individual, we talked about the radius, about the different elements. If we had element, let's say this was hydrogen and this was chlorine, all right? Those are the respective radius of that element. If we were to put them together to make this compound, which is a covalent compound because it involves nothing but nonmetals, hydrogen's a nonmetal, chlorine's a nonmetal, to generate HCl, which is hydrochloric acid or hydrogen chloride here, okay, which is what we find in our stomach. We would anticipate, it was anticipated that they would come together where, we're exaggerating, let me draw this a little better, where we have the hydrogen and then we have the chlorine coming together, where they would just touch together, and that would be the bond interaction. Well, in reality, that wasn't the case, okay? Let me explain here a little bit more. And so we have the hydrogen atom with its particular radius. Nm is nanometers. That's very tiny, 10 to the negative 9 meters. Okay. I'm sure you've heard of the term nanobots. We're down to the atomic scale. Okay. And then we have the radius of the chlorine. And we would anticipate that when they came together, it just simply be the sum of their individual radius, which is 0.136 nanometers. But in reality, in measuring and determining the radius between the hydrogen and the chlorine and as a compound, the actual radius was much less, 0.127 nanometers. And that is explained by the fact that those electrons that come together are actually being shared, and there's an overlap, okay? And there's an overlap between the two, between the hydrogen and the Cl, okay? And that is where that electron is being shared, two electrons in that bond, because if I were to draw this, I would just simply draw a line there to represent that bond, and there's overlap between the two. And because this is an example of a covalent bond. With an ionic bond, there wouldn't be any overlap. It would just simply be, as I was trying to draw, no overlap at all. If this was, let's say, sodium and this was the chloride, they would just be right up against each other, but be no overlap. Okay, and there's a difference between a ionic bond and versus a covalent bond. A covalent bond results in bond sharing and overlapping of that electron. Remember that we talked about the orbitals, okay, which will be on the scope here of how this is happening. But nevertheless, think about these orbitals that we just finished talking about. The hydrogen has an orbital, specifically the s orbital, right? The 1s has one electron in there. And then the chlorine, which is 3sp, 3p5, its orbital, it's going to come together, and that there's going to be some readjustment, if you will, okay? And so the orbital of the hydrogen will interact with the orbital, the p orbital of the chloride. There'll be some overlap. From a mathematical situation, the mathematical equations that describe these orbitals are rearranged make a new orbital and new mathematical equation, which accounts for the overlap, okay, and that bond between them. All right. So quickly about bond energy. Energy is required whenever we need to break or form a bond, okay? And when we are breaking a bond, anytime we need to break a bond, it always requires energy, okay? You're breaking a bond, so it's going to require energy to break that thing apart. And so energy in this case is considered a reactant, and it's absorbed from the environment. And that results in a type of reaction which is called endothermic. It literally gets cold. Yeah, because it's taking energy from the environment into the system or whatever the system is, and it becomes cold because that energy is being utilized to break that bond. A good example would be a cold pack. You could go to the pharmacy and buy a cold pack at the pharmacy. You get that pack and you smack it and it breaks up the chemicals inside. It gets cold. That is an example of an endothermic reaction. Endo meaning energy going into the system, okay? So the way we describe that as a chemical process is we have HCl, for example, hydrochloric acid, in this case, hydrogen chloride, plus heat, because heat is a reactant, and we break it up into the molecules, into the atoms themselves, okay? So we end up with hydrogen, and then chloride has 7 valence electrons, which I'm denoting here by the dots, okay? And I know it has 7 valence electrons, right? Because it's in group 7, and I can denote those 7 electrons by little dots, and that represents, those dots there represent the 7 valence electrons for chlorine, and then we know hydrogen has only one electron, so I just put 1 dot there. So I'm breaking that up, and you can tell here that these two are the ones that eventually share when they make a bond. Anyway, this is an example of a endothermic process. Now, when you bring atoms together to form a bond, okay, it releases energy. And so we call that exothermic process. Another classic example of this, again, back to the pharmacy. You buy a hot pack, you know, they got cold packs and hot packs. You buy the hot pack, smack the chemicals, it gets warm, okay? That is an example of an exothermic process, all right? Because something is being formed there and it's releasing energy. So in this case, energy is considered the product and it is being produced. So the reverse reaction that we just did is where you can get hydrogen atom, which again with 1 little dot there. Okay, let me change the color a little bit, make it yellow, you can really see it. Hydrogen has 1 little dot there, and chloride has 7 dots around it, right? 1 all by itself. And notice that they're gonna share here to form this bond. Okay. And so if I were to put the dots around, we're gonna have a lot more about these dots here in a second. It looks like that. That single bond. See that? And we form the bond. Heat is given off, making it an exothermic process. Okay. So breaking the bond is endothermic. We need heat to break that bond apart. And when they come together to form a bond, heat is given off. Okay. It's all by energy. I'm kind of introduced to you these electrons and these dots because we're gonna talk a lot more about that, but hopefully you can start picking up on how things how bonds are being made based on the valence electrons with respect to covalent compounds. All right. So with that in mind, and in this example, the question is electrons are shared in H2S. Now, again, you may not know what this compound is, but now I'm hoping by this time you can recognize the two atoms that are involved in this. And those two atoms are obviously hydrogen and sulfur to make this compound. And so the question is, electrons are shared, okay? And to be shared implies covalent. Remember that. Shared electrons means it's a covalent bond. And if they're covalent, what's the requirement for covalent? Non-metal versus and non-metal combination. Hydrogen's a non-metal, sulfur's a non-metal, okay? So this would be true. Oh, let me clear that up there. Okay, this statement would be a true statement. Okay, the bond between H and S is ionic. Okay, well, to answer that question, let's read the question carefully. In order to be an ionic bond requires a non-metal with a metal or metal non-metal combination, which is not the case with for H2S. So therefore, that comment is a false comment, okay? See what I'm trying to do here is to look at the question and break it down, you know, and answer it based on what we talked about so far, you know, systematic approach to get this and figure out the answer. All right, let's do this one. The HS bond length is less than the sum of the two atomic radii, okay? So in here, we are talking about the bond length between the hydrogen and sulfur. And if you recall from that slide, I mentioned with respect with ionic bonds, where we had, I wrote down, let's say that sodium and this is chloride. Okay, here's the sodium and this is the chloride. Well, you know, they got a full positive charge and a full negative charge. So they just come together like, you know, two balls coming together and just attract to each other, and that's it. I mentioned that covalent bonds are different. They actually share an electron, okay? They share electrons. And so that bond length between the two atoms is less, okay? And that is only true for covalent bonds. And this has to be true. Why? Because H and S are nonmetals, which are covalent nonmetals, which makes it a covalent bond. So this comment must be true, okay? It must be true because this is true. That comment isn't true for covalent compound. And then breaking the HS bond releases energy, and that's false, okay? Anytime you got to break the bond, I think breaking requires energy. Yeah, requires energy. All right, so that's our bit about energy and bond formation and so forth, and bond radius, which is going to get us into what we are called Lewis dot structures. Now, this is where we start learning how to determine the actual geometry of compounds, okay? But we do that, we're going to just talk about the atoms themselves. I just introduced to you the dots on the valence electrons, okay? Those are called Lewis dot structure, and just simply identifies the number of valence shells. And we already know that I can determine that by finding this position on the periodic table and what group it's in. Now, this is true only for the A metal, okay? The B metals, we cannot predict how many valence electrons they have. It varies. So the only ones we can predict are the A elements, okay? Keep that in mind. All right, so we just look at the group number. We talked about that, figuring out how many valence electrons they have, okay? And then think the way we do this, think of that element. We call it the symbol here, the element, and think of it as a block. Okay. Now, when we start adding electrons, we just go to one block and we go around the horn, fill each side first. So we're going to fill this. We go 1, 2, 3, and 4. So that would be an example of an element, 4 valence electrons. I went around all the sides. And now, as I fill them up, now whether I go clockwise, counterclockwise, makes no difference. Okay. So now if I go and I look for somebody who has 5 valence electrons, now I can double up and just keep going around the horn. So that represents 5 valence electrons, 6 valence electrons, 7 valence electrons, and then the noble gases. Okay. And so with just that block there, just temporary. So if I were to do that without the blocks, some people go 1, 2, 3, 4, 5, 6, 7, and 8. And these are Lewis dot structures. Okay. If we had one with 2 valence electrons, by convention, it would be incorrect to put them like this. Okay, that would be incorrect. If it's 2, you just put them, fill up the sides first. It's like filling up our orbitals, if you will. Start whichever side you pick makes no difference, whether it's on top, bottom, left, or right. But don't double up until you've gone around the horn, so to speak. All right. Okay. And so here, they ask you to do the Lewis dot structures for potassium. Okay. So we write down potassium. All right. Potassium is in group 1. So we can very quickly, bam, there we go. And that's it. Lewis dot structure. Okay. For potassium. Oxygen. Okay. Oxygen is in group 6. So we go 6 around. So we go 1, 2, 3, 4, 5, and 6. And there's oxygen right there. Okay. Remember, we go around the horn. Clockwise, counterclockwise, makes no difference. Silicon, it is in group 4. So we go 1, 2, 3, 4. Magnesium, okay. Magnesium's in group 2. So we can go 1, 2, or whichever place you want to put them, that's fine. I just, put them side by side just to be consistent with me going around the horn. And then iodine, okay, which is in group 7. We go 1, 2, 3, 4, 5, 6, and 7. So these are the Lewis dot structures for these elements. And, here's the interesting part. Potassium and sodium. Okay, sodium is in group 1, right? Just like potassium. Guess what? Its Lewis dot structure is that. Carbon's in group 4. Its Lewis dot structure for the atom is just like silicon. Okay. Remember, everybody in the same group shares the same number of valence electrons, denoted by the group number that they're in. Okay, which are denoted by the Roman numeral. All right, I just found out that I guess Roman numerals are not being taught as often as they used to. So very quickly, let me just, okay. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Our Roman numeral is a capital I. It is lowercase, but we use the capital is capital I. Roman numeral 2 is 2 as follows. 3 would be 3 lines. 4, we write the I, 1, and then the V. V represents 5. And if you put an I in front of the V, that means you subtract 1 to give you 4. If you put the 1 after the V, you add 1 to give you 6. Obviously, 7 would be 2 I's in front after the V, and 3 I's after the V for 8. Okay, and 10 is X, so therefore 9 would be I, and then the X. Okay, those are the Roman numerals. We only need to go to 6, but I threw in the other 3 as extra info. Which is interesting about Roman numerals because they do not have the concept of 0. Is not there in the Roman numerals. Fascinating. All right, so here we go. This is what I just went through with respect to the Lewis dot structure of the elements. Okay, knowing how many valence electrons each element has is quite important because we're going to take that information and use that to determine the type of geometry molecules we'll have. Okay, so which brings us to the Lewis dot structures. Okay, now the way we do this is one, you're always going to have a central atom, which we're going to tell you what the central atom. If we don't tell you, normally it is the first atom listed in the formula. For example, you might see like methane, okay, CH4. Well, the way it's written, you will find that the central atom is written first. So carbon will be the central atom, which tells you whatever follows will be bonded to the central atom. And we're going to underscore it to tell you what the central atom is, or the carbon may be written, C may be written bold, okay? Only exception to that is like water. By convention, water is always shown with H2O. It implies that hydrogen is the central atom. That's not the case. Oxygen is the central atom, and then hydrogens are bonded around, okay? So to draw Lewis dot structures, you have to, if you're not done so, make sure that obviously you're going to need the periodic table, okay? Because that's going to tell you, based on the A elements, only the number of valence electrons, okay? The other table is the shapes table. You're going to need this one, okay? Because based on what we're going to talk about here, we're going to generate a generic formula denoted by the letters A, B, and E. Okay, so I'm going to say A, B, and subscript X, and E, subscript Y. Okay, you're always going to have an A in general terms, meaning that's the central atom. We've got one central atom. B represents whatever's bonded to the central atom. Now, normally X can vary from 1 to 4, okay? So that's why I put a subscript. That number can vary to one item, or it could be 2, could be 3, could be up to 4. Some examples above that, but we're only going to go up to 4. And then E represents what we call the lone pair of electrons on the central atom. That's important. We're only talking about a lone pair on the central atom. You will find the other elements, B, will also have lone pair, but we're not concerned about that. Only what's in the central atom. And what do I mean by that? Well, like this one here. Look at this species right here. You have lone pair, that means 2 electrons, it's a pair. They're on the central atom. They're not bonded to anything, They are called non-bonding pair, okay? You sometimes have E's, sometimes you do not. At the most, you probably can end up with 2 E's, so that Y can become 2. All right, so once we have the general formula of ABE, we use this table to take us to the next step. We define what the geometry is for that particular species. So the most common geometry is something called the AB form, which is called, it has its own name, tetrahedron. And so here we have the central atom, and there are 4 species bonded to the central atom. And then we have denoted that line to be a bond between the central atom, and then we just call these guys X, whatever X may be. Well, I should have written B, but that's okay. Okay, there's 4 of them. Now, remember that that line represents 2 electrons, and there are 4 bonds around it. So those 2 electrons have a negative charge. So what's going to happen here, they're going to repel each other so that they're in the configuration that they are as far away from each other that they can physically be. And that's the case here. So that results in having this species with that pull away. If these were magnets that repelled each other, they would position themselves to be as far away from each other as possible, and they end up with that configuration. We call that tetrahedron. And then that bond angle between what is bonded to the central atom is what we call the bond angle. In this case, the most standard bond angle is 109.5 degrees. Okay. You can see some species have different bonds depending on what they are. Now, once we start working with lone pair in the central atom, our bond angle tends to change, because what's happening is these bond angles tend to occupy, you got 2 electrons here, okay? 2 electrons, negative charge, they're going to repel each other. The result is this bond angle gets pushed in because of the repulsion of 2 lone pairs on the central atom. So where we would anticipate 120 degrees, like here, it's actually less than 120 degrees because of the lone pair. And if we have more than 1 lone pair, that bond angle even gets less. And so if we look at something like this, with 2 lone pair, classic example of this species is H2O. We're going to go through all this. And we call that bent, that configuration. And that bond angle is much less than 109.5. That's our reference point, 109.5. And then we got lone pairs, those bond angles get to shrink, okay? So anyway, the point here is to figure out the general formula, which then gives us the name of the geometry, which then gives us the bond angle, okay? That's our ultimate goal of where we're going to go with this. All right, let's go back. So to do this, we're going to look at all the atoms in the molecule that you were given, okay? And identify how many of each atom. That's way back when we had a couple of examples of identify, for example, if you refresh your memory, PO4, here we had 3 hydrogens, 1 phosphorus, and 4 oxygens, okay? That is what that exercise is all about, to identify how many of each atom we have, okay? Once we know that, we go find out the number of valence electron each atom brings to the table, so to speak. Hydrogen brings 1, okay? And so, but there's 3 hydrogens, so we got a total of 3 valence electrons coming from the hydrogen. Phosphorus brings 5, right? Because it's in group 5, so it brings 5. Oxygen brings 6, and there's 4, so there's 24 valence electrons, okay? And so we tally this up. And so we got 9, 10, 11, 12. there are a total of 32 valence electrons involved with this particular formula right here. Okay, that is the number we got to work with. And the point here is this, that 32, that's it. You cannot, because if you cannot add more or you cannot subtract more, that is the number you got to work with, okay? And with that, we would tell you, okay, this is a central atom right here. So what that means is that that phosphorus is bonded to the central atom. I would give you more information with this particular structure. But the point here in this example is to identify how many atoms are involved, total, how many valence electrons each one brings in to the formula, and what is our total number of valence electrons. And that is what we work. Okay, then we'll tell you what is a central atom, and from there we're going to start building it and to create the general formula, which then would send us over to the other table, which will give us the molecular geometry. Okay, so we add up the total number of electrons. Okay, then we surround the central atom with all of the other atoms. We're going to draw, and then we can simply draw single lines to each of the other atoms to the central atom. Okay, we're going to tell you who the central atom is. It'll be either underlined or be in bold print. Okay, now we got to remember about the octet. When we start putting all these other atoms to the central atom, we take into account how many valence electrons we have to work with. Okay, and then take into account that all the atoms are striving to have 8 electrons around it to fulfill the octet, except hydrogen. Hydrogen only needs 2. Okay. And then we do a final check once you come up with the structure. Okay. And then from the central atom, we identify to see if there how many bonding pair, how many are bonded, and if any, how many unbonded are in there, or lone pair on the central atom, because that's going to help us identify the general formula ABE. And with that information, then we take the ABE to the shapes table. Okay. So let's do an example. An example here would be water, H2O. Okay. And so we have 2 hydrogens and 1 oxygen, right? Hydrogen each bring 1 valence electron. So we have a total, we got the valence electrons here. 2 of them are coming from both the hydrogens, and then oxygen is in group 6. So it brings 6 valence electrons, so it gives us a total of 8. That is the number we're working with. Now, what I like to do is I take that number and if that number should always be divisible by 2. Okay, because now I'm working with pair. If I divide that total number by 2, and now I got 4 pair to work with, and now I can just make a line and talk about a pair given the line. So oxygen is a central atom. So we can very quickly write oxygen and then draw a line for both those hydrogens. Okay, so that took care of 2 pair here and here. We have 4 pair to work with, so I can subtract 2 pair because I just used them up, leaving me with 2 pair to put someplace, right? Well, we know that hydrogen is the duet. So that line should tell you that hydrogen's happy now. I cannot put them on hydrogen. I cannot put any more on hydrogen because the duet has been fulfilled for both hydrogens. So the only logical place, but if you look at oxygen at this point, there are only 4 electrons around the oxygen, 2 with each hydrogen shared. So it stands to reason that 2 pair must go on the oxygens. Now, you have 2 choices here. You can draw a line like I just did, which is perfectly fine, or if you want, make 2 dots. And that's okay, you can do either one. Okay, now what we do here is we go check the total number of electrons of the pair that we have. So that took care of 2 pairs. So we're done there with the pair. Okay, so we've counted. So go back and count all of the electrons. We got 2, 4, 6, 8. Okay, 2, 4, 6, 8 electrons around oxygen. There's a total of 8 electrons. Okay, we have fulfilled, we've not done anything to change that number 8 that we come up with. That 4th pair could be either bonded pair or non-bonded pair. In this case, we have 2 that are bonded and 2 that are not bonded. So with respect to the general formula, it is A, which is the oxygen, B subscript 2, because there's 2 hydrogens bonded to the central atom. And in this case, we use the letter E, because remember the E represents a number of lone pair on the central atom. And that has a subscript of 2. So this is the general formula for water. Okay, AB2E2. We determine this from the valence electrons. We're given the formula and we determine the valence electrons, so then we can write the structure, determine what the structure is. Okay, which we just did right here, this part right here. Now with this general formula, AB2E2, we now go to the shapes table and look for AB2E2. And guess what? Here it is, AB2E2. That is the general formula for H2O, what we just did. Here's the geometry kind of drawn to you in kind of give it a 3D effect for you. That geometry is called bent, and that bond angle is less than 109.5. Don't forget the symbol less, because it's not 109. It's not 109. It is less than 109.5. So we have the oxygen with 2 lone pair, and then the 2 hydrogens. So this is the hydrogen, here's the hydrogen, and the oxygen in the center. Okay, and that is the formula, the structure for water. Given the valence electrons from that information, we were able to come to the shapes table to determine the geometry. Okay, and so this is a rehash of what I just did. Okay, and we got 8 electrons. The key is to keep track of your electrons as you start making the structures, and keep in mind that whatever number you come up with respect to valence electrons, that is a number you're going to work with. Also, another reason I like to divide by 2 was the fact that that number that you come up with should be divisible by 2. Okay, and yeah, it should be divisible by 2 as far as the total number of valence electrons. And there's the formula right there of water. Okay. Let's try these. Now, thing to remember about your valence electrons. Once you identified the central atom, once you put all the bonds in there and you used up all the valence electrons you come up with, and you check the octet and you find out, you know what? I'm shorthanded. I don't have enough electrons to get the octet. At that point, that's where you take electrons from one atom and you share it to create double bonds if necessary, and triple bonds is necessary. Okay, but you don't magically just pull out and make 2 more electrons. What you have to work with is what you have, and you create double bonds and triple bonds such such that the octet has been fulfilled. And this is a very good example of that. Okay. All right, let's take HCN, hydrogen cyanide, very poisonous gas. All right, so we have identified the atoms. We've got one hydrogen, one carbon, and one nitrogen. Okay. And so valence electrons, we got one coming from hydrogen, 4 from carbon, and 5 from nitrogen, right? So we got a total of 10 valence electrons or 5 pair to work. All right. You've been identified, the central atom has been identified, and that is carbon. So we can, and then the other 2 atoms are there. So we can quickly write carbon and then quickly take care of nitrogen and draw a line, take care of hydrogen. Okay. So that took care of 2 pairs. We got 3 pairs to work. Right. So those 3 pair work, then we put them. Well, obviously we can't put them on the hydrogen because hydrogen's happy. You can put them anywhere you want now. You can put them on the carbon or you can put them on the nitrogen. I just prefer to start with the outside atoms and work my way in. And in this case, I'm going to put those 3 pair, I'm going to put them around the nitrogen. And I'm just going to draw a line there. Okay, that line represents 3 pair. So that took care of my pair. All right. Now go back and do an inventory to make sure you have not violated the 5 pair and count to make sure you still have 5 pair. I got 1, 2, 3, 4, 5. Yes, double check. I still got 5 pair. Okay. You got to work with what you come up with respect to valence electrons. You can't magically just drop in a couple of electrons as needed. All right, now at this point, the next step is to check the octet/duet. Well, as I stated, hydrogen's okay. Nitrogen's happy, right? There's 8 around it. There's 8 electrons. They're happy. Nitrogen's happy. There's that word again, happy. There's 8 electrons around nitrogen, so that's been fulfilled. But count the ones around carbon. It only has 4. Okay. 4 electrons around carbon right now. There's 2 on the hydrogen, and there's 8 on the nitrogen. So nitrogen's okay, hydrogen's okay, except carbon. Now I cannot magically just pull out of the air, throwing electrons in. So this is where you get the electrons from the neighbor and you start making double bonds and triple bonds if necessary. So what I'm going to do is I'm going to take one of the pair on nitrogen, and I'm simply going to put it between the carbon and nitrogen and create a double bond. So here I'm going to give it a different color. So now I have a double bond nitrogen. I'm going to keep those lines there so you can see there. Now, double check, make sure you still got 5 pair. Got 1, 2, 3, 4, 5. Okay, I'm still good with 5 pair. All right, go back and check your octet. Nitrogen is still good. Okay, nitrogen has 2 pair that are not bonded, and then 2 pair that are bonded and shared with carbon. But now hydrogen's okay with 2 electrons. Okay, but carbon now has 6 electrons, so we're not there yet. Okay, so what we need to do is basically share again. Take from Peter, share with Paul, right? So we take another pair, and we'll take this one, and we're going to put it in there and make a triple bond. So now we got carbon, triple bond, nitrogen. We still got that lone pair there, and then the rest. Okay, double check your lines. 1, 2, 3, 4, 5. I've still got 5 pair. I'm still good. I didn't create new electrons, nor did I lose them. Okay. Now go back and check the octet. For nitrogen, there are 8 electrons total. One of them is a lone pair on nitrogen themselves, and then the other 6 are shared with the carbon, with that triple bond. Okay. So nitrogen's good. Carbon also has 8 electrons around. 6 of them are shared with the nitrogen, and 1 of them is shared with the hydrogen. So it's got 8. And then there's the 2 electrons for hydrogen, and so that's happy. So that is the formula. Let me redraw that. H, carbon, triple bond, nitrogen. Then I'm just a couple of dots there. Show you that. Okay, I still got 5 pairs, so we're good to go. Okay, my general formula would be A for the carbon and B2. Okay, B2 because I only have a hydrogen and a nitrogen bonded to the central atom. B can be the same element or they could be different. Makes no difference. Here and they're different, but nevertheless, there's 2 atoms bonded to the central atom. So our general formula is AB2. There's no E because there's no lone pair on the central atom. And we finish this and we'll be done. So that is our general formula for HCN, AB2. Now we go back to the shapes table, search for AB2, and sure enough, there it is right there. So here's the general formula for AB2. We have the carbon here, the nitrogen there, and the hydrogen there. That bond angle is 180 degrees, and the name for that particular shape is linear. Okay, it's a linear shape. All right. Okay, well, tell you what, let me stop it here.